An important question came up in class I'm going to answer here in this video. It's about example 4.2, Jacob's chapter 4, obviously. And it had to do with the fact that we have these two critical paths through the system. Which one are we concerned about? If you read in the book, actually, there's not really a strong answer to that. And they talk about is that you really have to look at everything. There's a lot of variability. We're going to talk about this here, and maybe it'll shed light on even the basic parts of the problem. But I'm starting here. This is the problem as given to us. Remember what we're doing here. We're doing a more realistic view of a critical path analysis called PERT, Program Evaluation and Review Technique. And you'd see this being done on large government projects, or any large project is continual reviews. Then they agree to a certain methodology about how they're going to do this, and this is exactly what they do. They come in and they have a nominal time here listed as these M values. They have an optimistic time and they have a pessimistic time, and everybody gets to know the language and the technique. And when you see a date estimate, you know that it's been done under PERT. You know how it's been done. Okay, so there are some people that got very good at estimating these times. Okay, so it has a lot to do with removing variability out of an estimate to a customer as to when something's going to be done on very sophisticated, complex projects, things like the space station and things like that. So starting with this kind of information, what we did was we did a network analysis through one of the critical paths, and what I'm going to do is go through that again and then show the alternate critical path and how does that affect our estimates. Okay, there will be a difference there because we have different variability involved with that. Okay, all right, so our network looks something like this. Okay, if you carefully look at the numbers, this network here is done out. It originally was done under the simple form here, without doing the time estimates, A through G. Okay, and then they gave us very strict, rigid. Here's our estimates: 21 weeks, 5 weeks. No variability in there. Nothing to say that you might finish early, you might finish late. Okay, and then this more complex problem when we do these estimates in here. When we do the calculations here, they conveniently chose the variable numbers so that the results, the expected times here, these ETs, okay, came out looking exactly like the first problem we have. In other words, now that you have these expected values, you're going to go through and you're going to analyze this network, right? Well, they carefully chose the numbers so that they came out exactly as they were before. But see, they're a function of variability here. They're a function that we calculated, this A plus 4M plus 4B, okay? And just to remind you there, it's a weighting. It's something to do about weighting inputs. Okay, we all do this every day. That equation can also be written 1/6 of an A plus 4/6 of an M plus 1/6 of a B. It's kind of like a recipe, all right? So you only add in 1/6 of an A, 1/6 of a B, and most of your recipe is going to have flour in it. So 4/6 of it is going to be your M. That's weighting. Okay, it's like making a recipe, some kind of dish, whatever you're going to cook. Okay, so it's kind of like the same thing. Let's go over to a live Excel sheet here, and we're going to remind ourselves of the equation. We're using some equations here. The end game, the end goal here is to be able to take a suggested time frame, or expected elapsed time, and figure out what the probability is of us being able to hit that exact amount of weeks. Okay, the idea here is to be able to say, if it did take 38 weeks to get through the network, okay, which is our network analysis, and we'd say it takes 38 weeks to get through here, and we had two critical paths, all right, what's the probability of us even hitting that 38th week? What's that probability? What if we could do it early? What if someone wanted to do it earlier? What's the probability of us hitting it earlier? Maybe they pay us a lot more to get it done a little bit earlier, which is a lot of the way road construction jobs are bid out. These monster bridges and other things like that are all bid out with incentives to finish early. Okay, so we were using our equations here. If you remember them, we'll find them again. Get the right page here. And if you do remember in class, I mentioned the version of this table that's printed in the book the one that I get as an instructor actually had an error up here. So this is supposed to be, all right, I need pen here. It's supposed to be over 6, not over 2. That's this equation here. All right, and the eventual equation that we do use is, we're using the z-scores here. Z-scores are just adjusted for a zero-based normal distribution. The expected value is 0, okay? And a z is multiple of a standard deviation, okay? If you look at the generic form of what a z-score is, you take some point of interest here, okay, pt of I, we're interested in this point, and you find the distance from that to your expected value, find that distance, and then you compare that distance to a standard deviation. What's the standard deviation of your data, okay? So if your point happened to be exactly one standard deviation away from the expected value, your average, you would just get sigma over sigma equals to 1. Okay, so z would be equal to 1 in this case. See, we're comparing the data that we have to an actual distance. The standard deviation is a distance. Remember, it's the average of the distances of every point away from the expected value. Okay, or it's like that. It's not precisely like that. Got to be careful about talking about that way, but that's how you can mentally imagine it. It's the average of how far all the points are from the expected value. Okay, so we need to know this. When you look this up in the table, our table in the back of the book goes from -4 to +4 z's. That means from -4 standard deviations to +4 standard deviations. When we get into Six Sigma, we would have to go out there a lot further than this, and you actually have to use Excel to calculate the values. Okay, but they give us a table here, and when you look that up, when you use a z-score into this, you're taking a look at a normal distribution, and let's say that our z-score is 1.25. So what does that mean? That means we want to know what the probability is that a sample point is up to and including this point on our data that correlates to 1.25 standard deviations. Okay, so we want to know the area under the curve is the probability. In a normal distribution, it's symmetric. 50% of your area is to the right, to the left of 0 point, and 50% is to the right. Okay, that's just some really quick review of the nature of normal data. And so when we look at 1.25, we're saying that the data point that we're interested in was 1.25 standard deviations to the right. Okay, it's positive. So we know it's greater than 50% because 50% comes up to 0, and then when we get up to 1.25, you'd only be guessing. I'd have to look at the table, but it'd be something, I don't know, maybe 75% or something like that. Okay, so a z-score of 1.25 might be something like 75%, or when you look it up in the table, it would be 0.75, like that. Let's go back to Excel and calculate some of these things. So we calculated our expected value by the equation that we were given, that I just went over, was give me 1 part of A, 4 parts of M, and 1 part of B. Divide that whole thing by 6, and these are our expected times. But the variance for any one of these processes is the B minus the A, so it's basically the distance from your longest time minus your shortest time. Your longest expected time or anticipated time would be 28, minus the A would be 10, so there's a difference of 18 weeks there. You divide by 6, that would be 3, and then you square it, and you would get 9. I have to get out of pen mode here. I'm sorry about that. Stuck in pen mode right now. I can't move that. There we go. Now we got it. So there's our 9. So we can reveal here that for every one of these processes, we use this data, and we calculate this variance here. Just remember that That's the variance, and the square root of your variance is your standard deviation. By definition, it's just defined that way. Okay, so we're calculating the variance here, and the ultimate equation that we're going to use, and I went over the z transform for a reason there, z score rather, is we're given this as part of PERT that z is equal to some time d, okay? That's our point of interest. Remember, I expressed that as a point of interest, minus our expected value of the path. So this is going to be the expected value of the entire critical path divided by, now we have a big equation here, it's going to be the sum, rather the square root of the sum of all the individual variances, which are the b minus a's, that's an a, squared, sum of all those. So we're going to figure out the variance for each of the processes in the critical path. We're going to add them together, and then we'll take the square root. And that's going to be the standard deviation for our problem here. This is given to us. You have to remember this, okay? When you solve one of these problems, we're given this is what you do in PERT. Okay, so we're going to come back over to Excel here. I'm going to calculate that. Sometimes it's good to see how to do it in Excel. Some of you might be very handy with this. But we'll take the b minus the a here. We need to divide by 6, but we have to take that whole thing to the square. So I use parens so we can keep the order straight here. There's no ambiguity as to what we want to do first. Okay, so we're going to raise that squared, and there's our 9. Okay, so we can drag this right down here. Okay, but if we go back to insert a column, actually I want to do that again. Insert another column here. I'll show you why. Because I want to show critical paths. We had 2 critical paths. Let's go back to our PowerPoint. We'll go in here. And if you look, we have an A, C, F, G critical path. And we have an A, B, D, F, G critical path. And in class and in the book, they solve for one and not the other. So the first one is we need an ACFG. So we'll do some colorizations here. ACFG, let's colorize that so we know that's one critical path. And then the other critical path would be an ABDFG. ABDFG, okay, and we'll color that something different. Great. Just clear that one out. I grabbed an extra one there. Okay. Because we only need the critical path. So we're going to do CP1, the first critical path, and then we'll calculate the second one, critical path 2. Okay. And we're going to calculate, we need to calculate the expected value, and we need to calculate that total variance. So what we need to do is, our estimated time is going to equal, and we already know this, the first one that we're going to do is going to be 21 and is 38 as we expected, and the expected time for the second one is going to be the same. We're saying that they're both critical paths, so I'm just going to grab both down, or not. Let's do our F4 shortcut here. Make them absolute references. We bring that down. So we have ET, expected time 1 and 2 are the same. That's the whole point here with 2 critical paths. All right. And then we'll do the critical path 1 variance, critical path 2. So the first one we're going to have 9 plus 0. It's the last one, right? So that's the first critical path. That's the critical path we did in class, and we should all recognize that. But here's the point, that there's another critical path. The book talks about it. All I'm going to do is calculate the other one. Okay, so the other one would be in green, you see? So the other critical path variance that we need to do is add A we're adding the green rows up for variance. And it's going to come out different. See? Now there's a difference. Now, the reason we're doing this is just what the book commented on, is that the variance through one of those paths is different than the other. Why? If we go back and look, you can see that for at least one reason, there's two more, in one critical path there's 4 activities, in the other critical path there's 5. There's a difference of 1 in number, but there's also 2 different activities in the second critical path here. Each of those, if you remember, if we go back to this sheet here, each of those has some kind of other behavior here. Each of those has different kind of estimates for optimistic and pessimistic, and that's why our variance over here, we get back to Excel, is different between the two of them. So what does that have to do with anything? Well, when we went back there and we calculated, we're going to calculate the z-score for this. We're going to have different numbers pop up here for the different paths. Okay? So when we look at this equation here, what's going to happen is the denominator is going to be different depending on which path we go through. So you're actually looking at 2 different paths have 2 different probabilities, and that's the issue. So let's do a calculation. Let's see if I can do this on the fly. What we need to do is, we were talking about 35 days. They want to know, can we get this out to a customer in 35 days? What's the probability of that? We were using the z-scores to do that. And so we're using this equation. And so I'm going to calculate it here. We're going to put in here probability of path 1 versus probability of path 2. Probability of path 1 is going to equal 35. We just know 35 minus 38. Those are going to be the same in both cases. Okay. We're going to have to use some parens here, keep the order of operation correct. And we're going to divide by, I need a paren here, there's path 1 variance. And we need to do the square root of that. So we're going to raise that to the 0.5. Minus 0.87. That sounds right. I think that's what we got in class. Okay. And now we can just take this and drag it right down. Well, look, now our z-scores. This is what we just calculated. I actually should name this as, I'm sorry, this should be the z-score that we just calculated. Not quite the probability there yet, right? Okay, so we just used this equation here, the z-score for path 1 and path 2. They're different. You go to look them up. I'm not going to go look the numbers up. I guess I will. Let me take a quick look here and see what the difference is. We knew the probability of this one up here was on the order of 19%. We had to do an interpolation in the table. And if we look up in Appendix G, minus 0.93, what is that close to? That's close to minus 0.1. And that's just an interesting point on our curve in the normal distribution, because it's around minus 1 standard deviations. If it were 1, minus 1, that means you're 1 standard deviation. We're minus 0.93 standard deviations away from the 0 point, and minus 0.93, when I look it up in the book, is interpolated between 18.5% and 17% roughly, okay? So this is approximately 17.17, something on the order of 1.775 probability. So depending on which path we go through, this is the big point of a great question that came up at the end of the class that we didn't have time to cover. I just wanted to get through the core, but here is your solution. Okay, so we did some recalculations here. It should help you be more familiar with it. And then we went beyond what the book was talking about, and we actually calculated the two different critical paths have a different influence on what we should tell our customer. Probably what we should probably say is use our worst case. That would be a strategy here. Is the worst case here would be there's more variability in the second path because there's two different activities in the second path than there were in the first, and there's one additional one. Okay, so there's actually 5 rather than 4 activities, and so that that's going to add more variation when you go through that. Each of these has some kind of bad variation in it, right? That causes us to be unsure of what we can promise a customer. So the worst case would be about 0.17, so we'd say about 17-18%. The other one is 19%, and then you might even put in a hedge value that you'd actually send to your client. You might pull back and you might hedge this even further for safety. But mathematically, scientifically speaking, one path, critical path through there, had a 19% chance of hitting 35 days, and the other one had 17.75% chance of hitting the 35 days. And just one last thing, okay, and I think it was an important observation, and I think we covered it in both sections. I just want to make sure everybody saw that. But when we do talk about this, and I explained it a little bit on this previous sheet here, when we looked at a normal distribution here, but I'm going to draw it again. All right, so what this says is if we did 100 programs, what are we really saying here? If we did 100 programs like this, we have a lot of history, okay? We've gained all this knowledge, and it says we can expect to, excuse me, pretty much get through here on 38 weeks. What is the probability that we do hit 38 weeks? Well, when we normalize this, go for the z-score, if z is equal to 0, 50% of the probability exists to the left of this point. That means the probability of hitting this number we felt pretty good about is only 50%. Just take that away. Hope you got a lot out of this, and it showed you more than the very specific topic we were after, but it should show you a little refresh about how to calculate some of these things. Have a good one.